You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Static analysis plays a critical role in modern cloud application development by offering a way to detect weaknesses early in the lifecycle, before code is ever executed. The purpose of this approach is to shift security to the left, embedding protective checks into the same stages where developers write and review code. Unlike dynamic testing, which requires running the application, static analysis examines the code base itself, searching for dangerous patterns, insecure functions, or overlooked validations. This method is particularly important in cloud applications, where deployment speed is high and mistakes can quickly propagate across distributed environments. Early detection saves time and cost by catching flaws when they are easiest to correct. More importantly, it strengthens resilience by preventing weak code from ever reaching production, where vulnerabilities could expose sensitive data or disrupt service continuity. Static application security testing, often abbreviated as SAST, is the formal name for this process of non-executing code analysis. In simple terms, it means scanning the source code without running it, using tools that identify security-relevant defects, such as input validation gaps, unsafe function calls, or weak error handling. By working directly with source files, SAST tools provide visibility at the earliest stages of development, allowing issues to be resolved before they become deeply embedded. Consider the analogy of proofreading a manuscript before it is printed. Errors are much cheaper to fix when caught in draft form than after thousands of copies have been shipped. SAST brings that same preventative advantage to cloud software, where every release carries potential security implications. To make findings understandable and actionable, many SAST tools align their results with Common Weakness Enumeration, or CWE identifiers. CWE is a standardized catalog of software weaknesses, such as buffer overflows or improper input validation. By mapping tool findings to CWE categories, developers and security professionals can quickly understand what type of problem they are dealing with and how it compares to known industry patterns. This shared language also enables organizations to track trends over time, benchmark themselves against peers, and prioritize fixes based on historical data. Without this mapping, raw findings may feel abstract or confusing, making remediation slower and less effective. Effectiveness in static analysis also depends heavily on language and framework coverage. A tool that excels in scanning Java code may not be effective in analyzing Python scripts or infrastructure as code templates. Since cloud applications often blend multiple languages and frameworks, front-end JavaScript, back-end microservices, and orchestration scripts, coverage breadth matters. Imagine a factory with multiple assembly lines. Inspecting only one line while ignoring the others leaves blind spots that attackers can exploit. Organizations must evaluate tools based not only on their headline capabilities but on their real-world ability to analyze the diverse codebases that make up cloud-native applications. One of the most sophisticated capabilities within SAST is taint analysis. Taint analysis works by tracing untrusted input sources, such as user forms or external APIs, through data flows and control paths until they reach sensitive operations known as sinks. If an unvalidated value travels from a web form directly into a database query, for example, the tool flags it as a possible SQL injection risk. This tracing is like following a drop of dye through a water system to see where it ends up. By modeling how data flows, taint analysis can uncover vulnerabilities that are not obvious from static inspection of individual lines of code, but emerge from the way code pieces interact. Static analysis is not limited to finding coding errors. It can also reveal embedded secrets. Secret detection scans for credentials, API keys, tokens, and private keys that developers may have accidentally hard-coded into source files or configuration artifacts. These secrets, if committed to version control, can leak into shared repositories, container images, or deployment logs. Automated detection ensures they are flagged and removed before they cause damage. For example, a developer might test an integration using a personal API key and forget to remove it before committing the code. Secret scanning prevents this oversight from turning into an exploitable entry point for attackers. Another dimension of static analysis comes from integrating software composition analysis, or SCA, into the workflow. While SAST focuses on internally written code, SCA examines external libraries and dependencies. By correlating code references with known vulnerable versions of dependencies, teams gain a holistic picture of their exposure. Imagine a developer writing safe application logic but relying on a flawed version of an encryption library. The security of the whole application is undermined. By layering SCA with SAST, organizations ensure that both their custom code and their imported code are scrutinized for weaknesses. Cloud applications increasingly rely on infrastructure as code, or IAC, templates to define their environments. Static checks for IAC ensure that insecure configurations are detected before they provision live resources. For instance, an IAC template might inadvertently create a storage bucket with public read access. By catching this in the template itself, organizations prevent insecure environments from being launched in the first place. IAC scanning extends static analysis beyond code logic to the infrastructure definitions that underpin cloud deployments, reinforcing the idea that security must cover the entire stack. SAST can also evaluate how developers use software development kits, or SDKs, particularly in cloud services. SDKs provide convenience functions, but sometimes ship with insecure defaults, such as weak transport settings or permissive access scopes. By scanning SDK usage, static analysis can identify where developers may have left default options in place or misconfigured client settings. For example, connecting to a cloud service without enabling encryption in transit might pass functional tests but still expose data to interception. Detecting insecure SDK configurations early ensures that developers adopt safe patterns consistently. Secure coding standards form the foundation for many static analysis checks. These standards define banned functions, required validation steps, and proper error handling practices that reduce risk. For example, a standard might prohibit the use of older, unsafe random number generators and require developers to use cryptographically secure alternatives. Static analysis tools can automatically enforce these standards by flagging violations. This creates consistency across teams and reduces reliance on individual developer memory. Much like building codes ensure that all contractors follow the same safety rules, secure coding standards ensure that applications meet baseline security expectations. Not every finding requires immediate action. Baseline and suppression workflows allow teams to manage acceptable risks without hiding new regressions. A baseline establishes the set of known issues that are tolerable, while suppressions temporarily mute findings that have a valid rationale. For example, a legacy application may contain code flagged as unsafe but mitigated by strong compensating controls. By tracking these exceptions, teams maintain focus on new or unexpected issues while documenting why certain findings remain unresolved. This balances pragmatism with progress, ensuring that developers are not overwhelmed by noise while still advancing security maturity. Differential scanning accelerates feedback by analyzing only the files and components changed since the last run. Instead of rescanning an entire codebase with each commit, tools can zero in on the areas impacted by recent edits. This approach reduces scan times, enabling integration into developer workflows without causing delays. Faster feedback means developers can fix issues while the changes are still fresh in their minds, increasing the likelihood of quick and effective remediation. It is similar to reviewing just the new edits in a draft rather than rereading an entire book each time an author makes changes. Static analysis integrates naturally into pre-commit hooks and continuous integration pipelines. Pre-commit hooks run lightweight checks on a developer's machine before changes are even shared. Continuous integration jobs take it further by running more comprehensive scans in the shared pipeline. This layered approach shifts detection as far left as possible, catching issues before they spread to others. It creates a culture where security checks are not an afterthought, but a routine part of the development cycle. Over time, this reduces the cost and impact of fixing vulnerabilities by embedding detection into everyday practices. To standardize results across different tools, many organizations rely on the Static Analysis Results Interchange Format, or SARIF. SARIF provides a consistent way to represent findings so that they can be aggregated in dashboards, correlated with other metrics, and tracked over time. Without such standardization, results from different tools may be difficult to combine or interpret, leading to duplication or confusion. SARIF enables interoperability, ensuring that static analysis becomes part of a unified security posture rather than a fragmented set of reports. Finally, finding triage is the process of evaluating results by assigning severity, likelihood, and exploitability within the business context. Not every flagged issue represents the same level of risk. For instance, an injection risk in a publicly exposed API is far more critical than one buried in an internal-only script. Triaging ensures that resources are directed where they matter most, balancing remediation efforts with business priorities. By incorporating exploitability and impact into prioritization, organizations avoid wasting time on low-value fixes while ensuring that genuine risks are addressed promptly. Developer enablement ties the whole process together by connecting findings with practical guidance. It is not enough to simply tell developers that a problem exists. Tools and processes should provide examples of safer code, references to secure libraries, and step-by-step remediation advice. By doing so, organizations turn security into a teaching opportunity rather than just a set of obstacles. Developers who understand not just what to fix but how to fix it are far more likely to adopt secure practices consistently. This feedback loop transforms static analysis from a compliance task into a true enabler of better, safer cloud applications. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Policy gates are one of the strongest ways to enforce the results of static analysis in practice. A policy gate is essentially a rule that blocks code merges or releases if the number or severity of findings exceeds a defined threshold. For example, an organization might decide that no high-severity security issues can be present before merging into the main branch. This transforms static analysis from a suggestion into a requirement. Much like a vehicle inspection that must be passed before a car can legally drive on the road, policy gates ensure only code that meets the baseline standard of security progresses to production. They provide a concrete enforcement point, aligning development speed with necessary guardrails. Branch protection rules extend this concept by tying SAST checks directly to repository workflows. These rules can require that static analysis passes before any pull request is merged into the main codebase. This prevents developers from bypassing checks in the name of speed and ensures that insecure code does not quietly slip through. When combined with automated scanning in the continuous integration pipeline, branch protection creates a consistent barrier against regressions. Developers quickly learn that resolving issues early is less disruptive than waiting for a failed merge, reinforcing a culture of secure coding. These rules embody the principle that code quality and security are inseparable from delivery. One of the persistent challenges in static analysis is managing false positives. Not every flagged issue is a genuine vulnerability, and if teams are overwhelmed by noise, they may start ignoring alerts altogether. False positive governance provides a structured way to handle this. Each dismissed finding must include documented rationale, context, and, ideally, an expiry date for reevaluation. This preserves the quality of the signal by ensuring that dismissals are transparent and temporary, not permanent silences. It is similar to marking an email as safe after careful review, but still revisiting that judgment later to confirm it is still valid. This discipline maintains trust in the scanning system over time. Custom rules add flexibility by allowing organizations to tailor static analysis to their unique needs. Out-of-the-box analyzers may not recognize risky patterns specific to in-house APIs or frameworks. By writing custom rules, security teams can capture these anti-patterns and ensure consistent detection. For example, a company might prohibit the direct use of a particular cryptographic library function due to known weaknesses, enforcing instead the use of an internal wrapper. By encoding this requirement into the scanner, the rule becomes enforceable at scale. Customization transforms static analysis from a generic tool into a context-aware guardian that understands the organization's specific risks and practices. Scaling static analysis across different repository structures introduces additional challenges. Some organizations favor monorepos, where all code lives in one repository, while others adopt polyrepos, where each service or component resides in its own repository. Each approach requires consistent baselines and clear ownership for findings. In a monorepo, central policies and automation can streamline scanning, but teams must coordinate across many contributors. In polyrepos, scanning must be distributed yet standardized, so that results remain comparable. Whichever model is used, the goal is the same: maintain coverage and accountability without creating bottlenecks or blind spots. As cloud applications expand into serverless and containerized architectures, static analysis must keep pace. Traditional tools designed for monolithic applications may miss the unique entry points of event-driven functions or container handlers. Ensuring that analyzers cover these code paths is vital, since they often act as the first line of interaction with external inputs. For instance, a serverless function triggered by an HTTP request must be scrutinized for injection risks, just as a traditional web controller would be. By explicitly configuring analyzers to scan these modern code paths, organizations ensure that their shift to new architectures does not inadvertently weaken their defenses. Cloud applications also span multiple languages, from front-end JavaScript to back-end Python or Java to infrastructure as code in YAML or Terraform. Multi-language pipelines orchestrate analyzers across these varied repositories to provide unified coverage. Rather than treating each language as a silo, these pipelines integrate results into a single dashboard, enabling holistic oversight. Without such orchestration, security visibility becomes fragmented, leaving teams blind to risks outside their primary domain. Multi-language scanning acknowledges the reality of cloud-native development. It is inherently polyglot, and security must adapt accordingly. Build reproducibility enhances the value of static analysis by ensuring that findings correlate consistently across environments. If two developers scan the same codebase, they should receive the same results. Deterministic builds, where the same inputs always yield the same outputs, underpin this consistency. Reproducibility removes ambiguity, allowing teams to trust that issues flagged in one environment truly exist in the code itself, not as artifacts of differences in setup. Inconsistent results undermine confidence in scanning, while reproducible analysis builds credibility and reliability over time. Metrics bring accountability to static analysis by making progress measurable. Common metrics include defect density, or the number of issues per 1,000 lines of code, mean time to remediate findings, and reintroduction rates, which track whether fixed issues return in later versions. By monitoring these indicators, organizations gain insight into whether their static analysis practices are actually reducing risk. For instance, a steadily declining defect density suggests that developers are learning and improving, while high reintroduction rates may signal the need for better education or process changes. Metrics transform static analysis from a reactive exercise into a continuous improvement loop. Static analysis findings can be powerful teaching moments when tied to secure coding education. By correlating common issues with targeted training, organizations help developers understand not only what to fix but why. For example, if cross-site scripting issues frequently appear, training sessions can focus on safe input handling in web frameworks. Embedding real examples from the team's own code makes the lessons more relevant and memorable. Over time, this closes the gap between detection and prevention, building a developer community that naturally avoids risky patterns rather than relying solely on automated tools. Governance and audit evidence formalize static analysis within broader compliance frameworks. Reports, policies, approvals, and change records provide proof that secure coding practices are enforced systematically. These artifacts matter not just for regulators but for internal stakeholders who need assurance that security is not an afterthought. Imagine a board of directors asking how the organization ensures cloud application safety. Being able to show structured policies backed by audit logs builds confidence in both the process and its outcomes. Governance turns security practices from implicit habits into explicit documented safeguards. Static analysis must also respect privacy by design. Some scans involve parsing large amounts of code and data, raising the risk of exposing sensitive information unnecessarily. Privacy by design scanning ensures that sensitive content is redacted, access is limited, and parsing is scoped appropriately. This prevents security tools themselves from becoming vectors of data leakage. For example, scanning tools should never replicate customer records into analysis environments. By minimizing unnecessary exposure, privacy-aware static analysis aligns with broader regulatory and ethical responsibilities. Scalability is another practical concern for large organizations with millions of lines of code. Static analysis tools must be tuned for concurrency, memory efficiency, and incremental indexing to handle massive repositories without grinding development to a halt. Incremental scanning, which focuses only on modified files, combined with parallel execution across multiple cores, can dramatically improve performance. This allows security to remain embedded without slowing productivity. Without scalability, static analysis risks being sidelined as too costly or time-consuming, undermining its very purpose. Success in static analysis should be measured not by the absence of findings, but by the stability of open issues, the timeliness of remediation, and the rarity of recurrence. Stabilized findings suggest that the backlog is under control. Timely remediation shows that issues are addressed before they can be exploited. Low recurrence rates indicate that lessons are sticking and developers are adopting secure habits. These criteria provide a realistic, outcome-driven view of success, emphasizing improvement over perfection. For learners preparing for exams, it is important to frame SAST as an assurance mechanism that provides early, verifiable confidence in code security. By integrating it with policy gates, branch protections, and metrics, organizations ensure that vulnerabilities are detected early and fixed effectively. Static analysis supports the broader principle of shifting left, making security part of the creative process rather than a separate afterthought. Understanding these practices not only prepares you for test questions, but also equips you with the mindset to design and maintain secure cloud applications in the real world. In summary, static analysis becomes a powerful enabler when combined with clear policies, meaningful metrics, and developer education. It ensures that weaknesses are caught early, that remediation is guided by business priorities, and that results are verifiable through governance and reproducibility. For cloud applications, where speed and complexity are constant pressures, SAST offers a disciplined way to balance innovation with assurance. By embedding static analysis into everyday development, organizations deliver cleaner code, stronger defenses, and greater confidence in their ability to withstand evolving threats. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.